Okay, so this summer as a part of the EBSCOR internship, I've been working on laser peening and sheet metal bending using a nanosecond pulse laser. This can be used for numerous different wind turbine components, and I've been working with PhD student Ningying Shen and Professor Hung-Tad Ding. So the motivation for this project has been to develop a process to improve wind turbine manufacturability, maintainability, and overall life of the whole machine, and also to develop a non-contact forming method for sheet metals to be bent, shaped, or precision aligned. And our technical approach has been first laser peening to improve the fatigue life of the component, and then laser forming for alignment and repair using the nanosecond laser. So materials and methods. First, the laser peening is a process of peening metals using a high energy pulse laser. It produces micro dimples in the surface, and this refines the microstructure and improves the surface lubrication. Compression with minimal cold working using these laser shock waves can help, as it's the same as regular peening, but without that cold working. So here's a little schematic to give you an idea of what exactly laser peening is. You have your nanosecond pulse laser coming in right here in the green with a water confining layer, and then this paint or aluminum foil which absorbs the energy and allows the shockwave to go into this target material right here, creating those micro dimples. And here's an example of what laser peening would look like on the surface. So here you have your dimples which refine the microstructure. So for sheet metal microbending, it uses the same idea as laser peening, but along the line that you'd have your laser peening, it would create a crease in the sheet metal. And as you can see, you'd have either positive bending angle, which we defined as towards the laser, or negative bending angle, which is away from the laser. Here's our lab setup. We have a schematic here in the corner. We have our laser that comes in, goes through a few different mirrors, and then is focused onto the target material. We have an XY axis stage that can move back and forth so we can get that peen along a line. And then here's our actual setup in the lab. As you can see, a lot more mirrors and optical lenses than in the schematic, but still the same idea. For our experimental conditions, we range the pulse energy from 0.2 to 0.75 joules and the thickness from 0.25 to 1.75 millimeters. We also varied the number of tracks, the scanning speed, and the overlapping ratio, which is just how the dimples overlap each other. And some of the most prevalent results that we got were that as you increase the specimen thickness or your target material's thickness, it goes from positive bending angle to negative bending angle. And as you can see, there's a lot more decrease in the angle as you get thicker. So our conclusions that we made are that for thin sheet metal, especially the 0.25 millimeter, you yield a positive bending angle and it's much more sensitive to an energy increase, while the thicker sheet metal at 1.75 millimeters yields a negative bending angle and is very insensitive to the energy increase. So moving forward, we've been working on a C code, which is an analytical model of the physics-based equations of laser peening. And we're trying to couple all that together to get a spatial distribution and time history of the pressure, velocity, and temperature that are induced on the target material. And that would just give us an idea of, as we change different parameters, what kind of changes we would see in those things. The pressure would tell us a lot about the peen that we would get and how good of a peen it would be, I guess. So the authors would like to acknowledge the material that's presented here is based on the EBSCOR grant. And thank you for your time.